Ladies and gentlemen, good afternoon. My name is Alexander Ilyin. I'm a first-year PhD student at St. Petersburg University, and I would like to introduce our report about stress-assisted corrosion of a toroidal shell under pressure. Let us start with some words about applicability of toroidal shells in engineering. Toroidal shells find many engineering applications, ranging from fuel tanks on rockets to turbine shrouds. Pipe bands and elbows, it is an important part of every piping system, and it also has the shape of the torus. All of the above structures are subjected to the action of mechanical loads and the aggressive action of gaseous, liquid, and solid media, such as water, fuel, gas, and so on. Simultaneous action of mechanical loads and aggressive environments can cause mechanochemical corrosion. The term mechanochemical corrosion was introduced with regard to general corrosion facilitated by stress, to be more precise, for anodic dissolution of elastically deformed metals. Corrosion may be defined as a general dissolution of the material with a rate V proportional to the maximum normal stress at a corresponding point of the inner surface. It can be described by formula presented on the slide. Here, A and M are empirically determined constants of the corrosion kinetics. In our study, we consider moderately non-uniform wear when we can neglect the change in the normal or to the corroding surface. This slide shows the general view of the geometry of considered toroidal shell. In our study, we consider the linearly elastic thick-walled shell under internal pressure. Here, R is so-called distance parameter, which is describes the distance between the torus center, axis of revolution A, and the tube center. In our study, we consider the two-dimensional axisymmetric problem for the cross-section of the torus loaded with a constant pressure on the involving internal boundary. Let us move to the model. The left-hand side presents the formulation of our finite element model. The problem is reduced to the two-dimensional axisymmetric problem for the cross-section of the torus loaded with a constant pressure on the involving internal boundary. In order to solve the boundary value problems with the priori unknown boundaries, the new APDL code was created and launched with via the ANSYS finite element software. The choice of the time step must be in agreement with the chosen step in space, or the mesh size, actually. Calculations were carried out for various time and spatial step sizes to ensure the obtained solution is mesh insensitive. This graph shows the growths of first principal stress at different nodes, actually marked by points with numbers, on the inner surface of the toroidal shell cross-section with time. As one can see, the greater the value of angle phi is, the higher is the first principal stress. The smallest stress is observed at 5 phi equals 0 degrees, and the largest at the 5 phi equals 180 degrees. It can be concluded that the service life of the toroidal shell is to be determined by the thickness and the stress value at this point, at point 61. In further analysis, we will analyze the stress growth at lifetime at the point 61. This graph shows the growth of the first principal stress at the node of our interest for various distance parameters R with time. Other parameters being equal, it can be noticed that the lower the distant parameter is, the higher is the rate of stress growth. From the presented graph, we can observe that for sufficiently large distance parameter, the results tend to the solution for a cylindrical pipe or perfect tube. Actually, let's go further. This graph shows the dependency of the service life of the toroidal shell on the initial relative stress, related to the ultimate stress, actually, for different pressures. Various values of the initial stress for each curve were obtained by variation of the initial stress thickness, other parameters being fixed. As one can see, at stress ratio equal to the constant value, a toroidal shell loaded with a higher pressure has a greater lifetime. This is due to the fact that in these conditions, shell under the higher pressures have a greater thickness. And it is also necessary to add something about the instability of solution. Relatively strong non-uniformity of the stress distribution leads to localization of the corrosive wear when the chosen model of the corrosion kinetics doesn't hold. Localization of corrosion is sufficiently thick wall shells occurs before any of the critical conditions, I mean reaching the maximum allowable stress or the minimum allowable thickness is met. Let's go to the conclusion. The service life of toroidal shell should be determined by the dissolution of the wall in the vicinity of the points closest to the shell axis. As the solution for the toroidal shell tends to the solution for a cylindrical pipe as the distance parameter R of the torus increases and other parameters being the same. It was observed that at an fixed initial safety coefficient, a toroidal shell loaded with a higher pressure has a greater service life due to the fact that under such conditions, shell under the higher pressure have a greater thickness. And also, again, some words about non-uniformity of stress distribution, which leads to the localization of corrosive wear when the chosen model of the corrosion kinetics doesn't hold, and about localization of corrosion, which is in sufficiently thick wall shells occurs before any of the critical conditions is met. Thank you for your attention.